In this video, you'll learn about how to model sedimentations in a detention pond or in a green infrastructures. Sedimentations are mostly relevant for sediment suspended particles or basically particles like microplastic or the normal sediments. So this is a picture of a detention pond where water comes in one locations and then that's basically as the water stands there, particles settle in towards the bottom of the pond. So this sedimentation rate is determined by particle size, water compositions, and the size or the shape of a swimming pool or the detention pond. And in principle, the larger the heavier particles, the faster it will settle inside the pond. So that means the sedimentation depends on size and density of particles. So how do you predict that? So that's based on the Stokes law. So Stokes law means that when you have a particles inside water, there are multiple forces that it will experience. First is gravity. So gravity is basically mass of the particles times the acceleration due to gravity, and mass of the particle you can determine based on the density. So that's basically volume of particles times density of particles. And volume of particles, if you are assuming it's a sphere, that will be 4 by 3 by r cube radius and all particles, and g is acceleration due to gravity. So that's just one force. What about the other forces? Other forces is buoyancy. Buoyancy is basically the weight of water it displaces. So that means you can write a buoyancy, which is the same way for the volume of water is 4 by 3 pi r cubed. And in this case, density will be density of water and acceleration due to gravity. So when you combine them together, this will determine the net force experienced by the particles. The third force is drag force. Basically, when the particle is moving, there is a frictional force on the side of the particles. That is 6 pi mu r velocity of sedimentation. So this mu or this one is basically the viscosity of water. This is viscosity of water. So when the particle is settling at net force equal to 0, then you can estimate the velocity of settling. And the velocity of settling, when you rearrange them, is basically this value. Is a function of. So what it means is velocity of particle is a function of the size of particle to the power square. So that means that the size of the particle increases, this is more likely the velocity will increase much faster. That's why the large particles settle much faster. This is also proportional to the difference in density of particle with respect to the water. So that's basically delta density, or which is basically density of particles minus density of water. So if you know the density difference, that's why the heavier or denser particles is going to settle much faster. And then it's inversely proportional to the viscosity. Viscosity is basically, it creates the friction force. If there is more viscous, particle will not settle quickly. So combining all those things, we'll be able to predict the velocity of settling. But detention pond, this all it tells about the how quickly it settles, but it doesn't say about whether this particle will settle before the water overflow into outside. So that's why it's important to measure the overflow rate. What is overflow rate? Think of this as like a simple tank, and you have a area here, and water is flowing inside it, or water is going inside it. So the overflow rate is basically how much water you are overflowing inside the systems, and that overflow rate is basically the flow rate, how much water overflow, divided by the area, the surface area of the water, or the area of the pond to which it overflow. So overflow rate is basically, I can write that this velocity of overflow is flow rate divided by area of the pond, top area of the pond where overflow occurs. So if you compare overflow rate, the overflow rate has to be smaller than the sedimentation rate for a particle to settle. If the particle settle much faster before it overflow, then you know that most of the particles are removed. If particles settle at much slower rate than the overflow rate, then you know that some other fraction of the particles will leave the systems. So percentage particles removed is basically ratio of the particles velocity or settling velocity by overflow velocity. So percentage removed is the velocity of settling by velocity of overflow times. All right, so based on that, you learn that this is the process you can use to calculate settling velocity. And so here is a quiz question. So quiz question is, which of the following factor would increase the settling velocity? So you can think of this one for a second, and then we can answer these questions. Right, so the answer, which of the following factors would increase settling velocity, is the answer is A. The reason is if you increase the particle size, is the weight of the particles is not increased, and so that means you are going to increase the settling velocity times particle size to the power square. Increased viscosity decreases, increase in depth is not affecting the settling velocity. So based on that, let's solve these questions. It says that determine the percentage of suspended sediments with the size 10 micrometers and specific gravity of 1.4 would be removed by a detention pond of certain size, which is 30 meter by 30 meter by 1 meter, receiving stormwater at a rate of 7,500 cubic meters per day. Viscosity of water is given. Right, so it's saying that how much percentage of the sediment particle with size 10 micrometers will be removed. So here is a one from specific gravity is 1.4. So what that means is specific gravity means specific gravity, which is basically density of particles by density of water, which is 1.4. So that means now the particle is 40% more heavier than water. So now the detention pond is 30 by 30 meters. So that means you can write that the area of the pond is basically 30 times 30. So area is 30 by 30. So this is going to be 900 square meter. So now the percentage of suspended sediments removed is based on the formula just we calculated. So that's velocity of particles by velocity of overflow rate. So overflow rate from here. So that means percentage removed is velocity of settling by overflow rate. And if you know the velocity of a particle is a dp square density of particles minus density of water times g divided by 18 times viscosity. And the velocity of overflow rate, you know that, is basically flow rates divided by the size of area of the pools or the area of the pond. So if you do this one, this is basically going to become, if you reverse it, that's going to be Q area. So if you put this value, dP is given, that's 10 microns. So that's basically 10 times 10 to the power minus 6 meters. So that's square, meter square. It's important to write all the units. And now the density of water particle is 1.4 times density of water. So that means it is 1.4 minus 1. That's basically, and then density of water. Density of water, you can times G divided by 18. And the viscosity is given is 0.001002 kilogram meter second. And then the flow rate is 750 cubic meter per day. So now the you have to multiply area also on the top. So that's basically, let's write all those things. So when you write, we want to write Q, let's say area, let's write everything, each of them. I'm just going to erase this one. Density of water is is 1000 kilogram per meter cube. That's density. And then you have acceleration due to gravity 9.8 meter per second square. And then area is 900 meters square. So if you see meter square, meter cube, all these things exist. The only difference here is that kilograms, meter, there is a day here. So that means you have to change the day to second. One day is 24 hours and each hour is at 60 minutes and each minute is 60 seconds. So now this whole terms will give you percentage of particles removed. So the point here is that if you know all this number, you will be able to calculate the percentage particles removed. Then another question was, if you think of other way, if you know the removal rate, then you'll be able to calculate the size of the particle that can be removed completely. So this is the question here. Determine the smallest size of suspended sediment with a specific gravity of 1 pole that would be completely removed by the detention pond, which is given before, if we are the same case. So now think of this. Here it says that smallest size particle completely removed. The complete remove means that the removal is 100%. What that means is percentage removal 100% means your overflow rates is the same as, or overflow rate divided by the settling velocity by overflow rate is 1, means 100% particles is removed. So that means you can think of that as a B overflow rate is the same as settling velocity. If that's the case, you can solve for the unknown variables of the size. So that's what we did here. So settling velocity is this. The left side is settling velocity, right side is overflow rates. When you combine them and solve for D, you get this number. So that means you can solve exactly the same thing. Is 900 Q is 750 750 meter cube per day, and then again 1 day is same as 24 hours times 60 minutes times 60 seconds. That's the cubic meter per second. Area is 900 square meters, and 18 times mu is given. That value is given is 0.001, 0.001002. That's kilogram per meter per second. So kilogram per meter per second, and that's basically the viscosity divided by acceleration due to gravity, 9.8 meter per second square, and then 1.4 minus 1. That's basically the how difference in density, and density of water is 1000 kilogram per meter cube. So when you solve for this one, you'll get a size in a meter, and that will determine the smallest size particle that can be removed. So there is another book, another question that was given in the examples, which is in the book. So I encourage you to read that examples, and the solution is given. And these two examples are more realistic, and you can use that. It's the same concept, and you can use this to solve it. So I encourage you to check these examples.